Hey Gen Chem class, so we are going to talk about chapter 14, which is the Kinetics chapter, okay? The best way to use these videos, in my opinion, in my experience, is to print these notes, okay? So pause the video if you haven't done that, and then fill them in as we go along in the video, making sure that you write down any questions you have, and circle them, and star them, and highlight them so you remember to ask them in class. All right, so we're going to start with just a brief introduction. What is kinetics? Why do we care? Etc. The thing here is essentially that kinetics studies how fast reactions occur. So we've done some, work with thermodynamics, which is really about studying how much energy things require and whether or not they can happen at all. So when you think about thermodynamics like calorimetry, Hess's law, all of that stuff, it's really about, does the reaction happen or not? Okay, and we're going to dive back into that in later chapters, all right? But for now, we need to understand that thermodynamics does not tell us how fast a reaction occurs. It just tells us, does the reaction happen? Kinetics is how we figure out speed of a reaction, the rate of a reaction, okay? So just to clarify the relationship between rate and time, if something has a fast rate, it means time is short. If it has a slow rate, time is long, all right? So let me get this out of the way. So when we look at these examples, exciting an electron from the ground state to the first energy level, the first excited energy level, takes a fraction of a second. So this is a really short period of time, which means the rate is very high, right? So inverse, that's the inverse relationship. Here we have an explosion, takes about 1 second for that reaction to happen, which is obviously quick. We can't even perceive 10 to the negative 15 seconds. We can't really understand that. But 1 second is an understandable quantity. So that's pretty fast. That's a pretty fast reaction. Certainly the ones that we do in the chemistry lab tend to be between, the explosion level and rusting an entire ship, which takes a long time, 30 years, right? So that would mean that the rate of reaction for a ship rusting is really, really small, and that means it takes a long time to do it. And even more than that is, geologic processes. They take millions of years to do. All right, so these are all reactions that thermodynamics says are spontaneous, right, meaning it happens, but they happen at different speeds, and that's the part where kinetics comes in. Okay, so the rate of a reaction, how fast it goes, depends on a couple of factors. Number one, how often things collide. Number two, the relative amount of collisions with enough energy to break. Like if things are colliding frequently but slowly, they have a tendency to not have enough energy to break the bonds, and what you get is no reaction after all. So that is shown in example D here. We're trying to make CO2, so we have carbon monoxide, oxygen and carbon, with NO2, right? So this is CO, this is NO2. And when these things collide in exactly the right way with enough energy, right, so it's 0.2, they will exchange this oxygen over to the carbon, and you get CO2 and NO, okay? However, even when they're oriented correctly, it is very possible to collide sort of slow and not have enough energy. And if you don't have enough energy to break the NO bond, then they're just going to rebound and go about their business. And so you basically don't get a reaction at all. Number three is about orientation. Okay, so like, for example, if two oxygens come together, they are both very electronegative, which means they usually have about 4 unpaired electrons kind of hanging out on this sort of side. And so if those 4 electrons come near each other, they're not going to want to hang out there. They're going to repel, which means that the atoms don't get close enough to trade oxygen to the carbon. Okay. Another possible incorrect orientation is if the oxygen on the carbon is oriented toward the nitrogen. Okay, so this is less about repulsion and more about not having enough energy to break the CO bond, which is a stronger bond than NO. Okay. Finally, if we collide in the right orientation where carbon is facing the oxygen on NO2, it's going to form what we call an activated complex, which has two kind of synonyms for that. Sometimes we call them transition states. Okay, those are very temporary. They go away almost too fast to measure. If it sticks around a little bit longer, sometimes we So transition states don't, they last a little bit longer. They don't go away as quickly. But another synonym for activated complex, which again, these are always unstable, it's just a matter of how long they stay around. Another name for transition state and activated complex is intermediate. Intermediates tend to be really short-lived. Okay, so they go away almost too soon to measure, whereas transition states have a habit of hanging around for a little bit. Okay, so we have this transition state that forms. That's crucial. You have to have kind of like a half a bond to the carbon and a half a bond to the nitrogen, because it weakens by doing this. It's weakening the NO bond, and since we said CO is a strong bond, that one's not going to break, whereas the NO bond is weaker, so it's the one that breaks. Okay, so we get products if it has enough energy and it's oriented precisely correct. That means that anything we do to change these three factors is going to change the rate of the reaction. So here's some details about that. All right, so basically, the more collisions we get, the faster the reaction goes. All right, and so when we think about a solid, solids don't move very much, so they have very few collisions. This is why geologic processes take millions of years. We do most of our chemistry in the lab in the liquid phase. That's because the reactions happen at a relatively quick rate, but not so fast that we can't see anything. Gases tend to react really, really quickly because they're moving around so fast already. When they collide, they have lots of energy, so high rate, generally speaking. Concentration matters too. If you have more particles present, it is likely they're going to run into each other more frequently. So it makes sense that having a high concentration would increase the rate of reaction. Also, if I heat it up, right, reactions go faster when they're hot. Almost always, not always, but generally speaking, if we increase kinetic energy, the particles are moving faster, which means more collisions, which means the rate is faster. Our final tactic is to add a catalyst. A catalyst is something that speeds up a reaction, is not consumed. Right? So when we use a catalyst, usually we write it over the arrow. So here's an example. You can decompose hydrogen peroxide by adding, it decomposes on its own. That's why it expires and it's stored in a brown bottle. But if you add a little bit of MnO2, it's a black powder, it will accelerate this decomposition very quickly, so you can actually see the oxygen forming rather than, you know, waiting forever. Oops. That was wrong. Okay, so you make 2 water and one oxygen gas. So the catalyst is written over the arrow because it's not consumed, so I wouldn't write it as a reactant. Or if I did, it would also be a product, which is kind of awkward. But it's an important thing to note because without the catalyst, this process can take years to convert all of the hydrogen peroxide into oxygen and water. But with this catalyst, it happens in a matter of minutes. Okay. Catalysts typically work by changing the orientation of the molecules. All right, so that means holding them in place so they are inclined to react more quickly. All right, so here's an example of that. In biology, we have tons and tons of catalysts. They're mostly called enzymes. Enzymes are mostly made of proteins, not always. Some RNA can make it. And one example is something called telomerase. Telomerase is pretty interesting. It adds a whole bunch of extra pieces at the end of DNA to protect the important information, right? So it just adds some like nonsense onto the end because the ends of DNA are vulnerable to oxidation and other mutation problems. So telomerase is cool because it just sticks on a bunch of extra stuff. And what it has to do that is hold some RNA in place so that it's oriented exactly right. Normally RNA has a habit of folding up and looking basically like that. Okay, so it just folds up in really weird ways. It's not as organized as DNA is. DNA gets this nice double helix, but RNA has a tendency to just be like a mess. And so in order, it would be really hard to get your reaction to happen when you've got to get the chemicals that are kind of pointing in the middle here to connect with other things, right? So in order to facilitate this, telomerase kind of threads the RNA through it and kind of creates this availability so that the DNA template can be extended by just matching complementary pair to the RNA that's kind of being used as a template inside of the telomerase. Okay. So, the cool thing is, after this is done, after all this telomeres are filled at the end of this DNA piece, this telomerase is going to fall off and go on to another piece of DNA and protect that one. It's not consumed. This works by lowering the activation energy of a reaction. So if we think about a reaction diagram, if I wanted to do, making this DNA, so we're starting with our reactants here. If I wanted to do this reaction without a catalyst, that would be the red. Okay, it might look something like that. Products are lower than reactants, so that's an exothermic reaction here. But if a catalyst is added, such as a telomerase or any other enzyme, well, those are supposed to line up down here. Hang on. There we go. Close enough. What it does is it lowers the amount of energy that's required to get the reaction up this hill. So this is called activation energy, which is abbreviated EA. In other words, the energy to activate something. And when you have a catalyst, the EA is smaller than when you don't. That's because it's positioned correctly, so it takes less energy to do the reaction. Okay. So use catalysts all the time, not just your body has catalysts, but also things like catalytic converter in your car is literally a platinum solid that captures the carbon monoxide gas that flows over top of it and turns it into CO2, which is a lot less toxic. Okay. All right, so catalysts are everywhere. They're your friend. They help you out. So now let's take a look at how do we measure the rate of a reaction. Okay. So our reaction is pretty simple. We're starting off with all A, 1 mole of A in a container, and it's going to convert to B. So it's like the simplest kind of reaction you can have. A fake one, because not very many things actually do something that's simple. So we're starting with A to B. And so at 0 seconds, I'm going to put the time in the top because that's a lot easier than writing it 100 times. So at 0 seconds, we have 100% A. So if I assume my flask is 1 liter, then I could write it's 1 molar. I don't have to have a unit there because I have it up here. Oops. And the concentration of B, of course, is 0 molar. After 20 seconds, our concentration has become a little less clean, 0.54 molar A and 0.46 molar B. So now we have a mixture. Still running the M. I really don't need to do that. Doing extra work. And with the seconds too. What a mess. All right, so we have the next time point is at 40 seconds. I'm going to make this look neat. There we go. A little bit better. So at 40 seconds, we have 0.3 moles. Oh, those are different colors. And 0.70 moles of B. So we have monitored the time and the concentration as it changes over time. So that's the first step. That's what we do in the lab. All right. So we measure the time and find a way to measure the concentration change over time. Now, to find the rate, we can either look at how quickly there's a decrease in reactant. So it would be something like the change in concentration of A divided by the change in time. Time is actually a lowercase t, so there we go. So like from 0 to 20 seconds, it would be 1.00 minus 0.54 molar divided by 20 seconds, right? From 20 minus 0 is how I got that. All right, this is a negative change because it's decreasing over time. All right, so since if I'm watching a reactant disappear, that's a negative. Okay, so the rate equals negative change in concentration of A divided by change in time. If I wanted to look at B in the same time interval, the rate would be equal to a positive value this time because it's increasing. So we're going to go the change in concentration of B. Well, that's easy. It goes from 0 to 0.46 molar, and it's the same time interval. Okay, so the units for a rate are a little odd. It's concentration over time, typically. So if we do this math, we're going to find that the rate according to watching the product disappear is going to be negative 0.023. Oh, you know what? Actually, I'm sorry, I did this wrong. Okay, so if it's an interval of 20 seconds, we did 20 minus 0 to get that. So in order to get this correct, I have to do the same order. It's kind of like a slope calculation, right? I got to go 0.54 minus 1. Right, so now the negative sign in the rate is negative of a negative, so this is going to become a positive value. And our unit is molar per second. Up here we get the same exact number. Alright, and so that's why the signs are important. So I'm going to go through this just one more time for the next interval so you can really understand it, since I confused the signs there. So for the 20 to 40 second interval, the concentration change of A goes, so we go final minus initial is the idea. And this is our final, this is our initial. So we go 0.30 minus 0.54. And you do the same thing for the temperature. Okay. And this whole thing is a negative as well. So the temperature is 40, sorry, the time I meant, 40 minus 20. Okay. And interestingly, what we see here is a different value, same units because it's mole on top, I didn't write it in seconds there. It's a different value, but that sort of makes some sense because we said as concentration of the reactant decreases, the reaction rate would decrease. Or if we had a higher concentration, it would increase, right? So we have the highest concentration in the beginning. And as we go along, it gets slower and slower because there's less A around. Okay? So this is how we calculate rates. It's a function of the change in concentration over time. If you're monitoring the reactant disappearing, then it's negative of that ratio. If you're monitoring the appearance of product, then it's positive. Okay, so this is basically summarizing that idea here. Okay. These two rates are identical. So what we got in the first example, here was 0.023 for both of them. All right. So the lesson here is it doesn't matter which one you do, whether you watch A disappear or whether you watch B appear. In either case, it's going to give you the same rate. Okay. The choice comes in because some of the time the product might be easier to measure, might be easier to tell how much you have. Maybe it's something that turns color, and you can use a spectrophotometer to measure the color change, something like that. Okay. Maybe the appearance of a precipitate. Those kind of things are a way to track your products and reactants. All right, so here's a set of data for this reaction. We've measured the rate, so they did that calculation, the change in concentration over time. And as it turns out, the rate is decreasing as we go down this list. And that's because the amount of reactant, this reactant they've outlined here, but both of them decrease over time a bit. The reactant is decreasing as we go along, which means the concentration is lower, which means there's less frequent collisions. So this creates a situation where we have to measure things in the very beginning of a reaction. This is the fastest rate. This is the most accurate rate for the concentration of reactant that we have put in. it changes very rapidly. The concentration changes very rapidly after that, and it decreases the rate as we do. So the method we use is not very cleverly named, but it does tell you what it's for. It's the method of initial rates. It accounts for the fact that concentrations are changing quickly, and so we want to use just sort of the beginning data, because that's the one where the concentration is as close to your beginning state as possible. Okay, and when we do the method of initial rates, our ultimate goal is to try and get something that looks like this. This is called a rate law. Okay, it defines how different reactants affect the reactant as a whole. Okay, so here's our generic reaction, right? The little ones are coefficient, the big letters are the chemicals, or the, elements, whatever they are. So we've made sort of a generic statement here. The rate law does not have anything about the products in it. It's just about the reactants, and it has this constant, K. We call that the rate constant. K is the same if the conditions are the same, things like temperature and catalyst presence, all that kind of thing is held the same. Then K will be the same for different concentrations. X and Y are going to be whole numbers. They're called rate order, and they're always whole numbers, so 1, 2, or 3 is pretty much it. And really the method of initial rates is made so we can find X's, Y's, and K's. That's our goal. So we measure the rate in the lab. We figure out K based on our measurements. We figure out X and Y based on our measurements. And we already know the concentration of A and the concentration of B. Oh, a reminder, these brackets mean molarity. Okay, so we're talking about concentration of the reactants here. You measure the rate, and you can use that same formula to compute just like this, right? The little a represents the coefficient. So if we have like a 2-to-1 reaction or something, you got to consider that. Okay, so here's our formula for this side of the reaction, of the equation, and we would know a and b, and you can manipulate things to solve kx and y. So we have a 3-variable problem here. Okay. The important thing is, if A goes up, the rate goes up. If B goes up, the rate goes up. Assuming that, oh, that reminds me, X and Y can also be 0. Right? So if these are not 0, then the concentration depends on, the rate depends on the concentration. Oh, the last bullet's kind of important. Why? How is the rate law important? How is it used? So let's say we invent some kind of chemical reaction to create something really awesome, like a great medicine to cure cancer. All right. It only does any good if you can make enough of it in a reasonable period of time to market it, to be able to get it to people. Okay. So if the reaction takes 1,000 years to make one, dose, that's probably not going to work. We need to find a catalyst. All right. Or we need to play with the conditions to make collisions happen more often. So that's one application. So this method of initial rates thing is made to find k, x, and y. So it's a 3-variable problem. Okay. You should be able to answer this question, so take a second, jot that down. You can pause the video, answer why it's important to do it at the beginning of the reaction. Okay. Here's a visual representation of y. This is the rate of the reaction plotted on a graph of concentration versus time. So as concentration decreases, the rate starts to flatten out. Okay. It turns out in the beginning, it's basically a line. Okay. We call that the initial rate, where it follows the linear equation here. But once the reactant starts to get used up, it starts to flatten out. Okay. And we can't really do a kinetic study down in this area, because of the simple fact that you can't generate a very good line, an equation for this line. So there's not a lot of valuable information in that part of the curve. But if we can isolate ourselves to the beginning where it's linear, we can get some really good data. So here's an example. We've set up 3 reactions. This is, by the way, taken from your kinetics experiment. It's only one step out of several. So I don't want you to think that this is the only thing that's happening. It's more complex than that. All right. So, and just so we're clear on the lingo, this is per sulfate, S2O8. And this, of course, is sulfate. Okay, there's another one in your lab that we're going to run into. This is thiosulfate. Okay, so these are good things to like be very familiar with before you do the kinetics experiment, because they're all going to come up. Okay, so what we've done is arranged 3 experiments, and these concentrations are specifically chosen so that 2 of the persulfate ion concentrations are identical, and we vary the amount of I3 minus, which, by the way, just so you know, that is an iodide ion. Nope, sorry, that was wrong. There's 3 iodines, so it's triiodide. Iodide would just be I minus. All right, it's regular iodine as an ion. Okay, so triiodide ion. We vary that one. No, wait, this is wrong. We're varying I. I don't know why there's a 3 there. We're varying I minus. We vary the reactant. Okay, that was my confusion. I'm sorry. So iodide ion reacts with persulfate ion. So when we're going to be changing, we're looking at the amount of persulfate and iodide. We're tracking disappearance here. So we have 2 reactions where iodide is constant, and 2 reactions where persulfate is constant. All right. So you'll see, like here and here, this is where the iodide is constant, and the persulfate is in green. All right. So this is structured very carefully to have this pattern. Okay. So when you're given a bunch of data and you got to calculate this on your own, you need to look for the reactions where one of the reagents is the same and the other one is varied. So here's how we're going to do it. First, we're going to write a general statement about the rate. Okay, and this is just so we're set up and we know what we're talking about. And it comes from the balanced reaction, and it comes from sort of our statement on the other page about what a rate law looks like. So K is always there. It's going to be a number eventually, but right now it's just K. And instead of writing A and B, I'm going to actually separate these out. Okay, so what we have here is we've substituted the actual reactants in. No products enter into this. And we are assigning the variable X to the persulfate and I minus to iodide. It doesn't really matter which one you put where. We just want to have a definition. It's defining our goal here. All right, and the second step is we're going to compare the rate laws that are the same. So like, for example, we could do the 2 green ones first. It doesn't really matter which one we pick first. All right, and when I say compare, what I mean is we're going to make a ratio. So the rate of reaction 1 divided by the rate of reaction 3 is going to be how we compare the ones where thiosulfate is, or sorry, persulfate is the same. And so we're going to write the same thing, K. This time I'm going to substitute for the actual molarity here. Okay, so S2O8 is 0.042 molar. And that's raised to the X. I minus is 0.084 molar, and that's raised to the Y. And then on the bottom we do the same thing, but for the rate 3. I'm going to stop writing the units. I don't want you to be confused by the units, so I'm going to write with ignoring molarity for a minute. So X is on the top, and then we have 0.042 molar for our H or I minus concentration here. Okay, so we know the rates, and so I'm going to go ahead, instead of writing just rate 1 and rate 3, I'm going to expand on this a little bit and write the actual value here. So this has been measured by monitoring concentration of either a reactant disappearing or a product appearing, and then dividing by time. And so that's just a number, right? And so what we find is that on the left-hand side of, well, the middle actually, in the middle of our equation, this is going to simplify quite a bit. All right, so K's are the same no matter what the concentrations are, so those cancel out. 0.042 raised to the X is the same on the top and the bottom, so those cancel out. So that just leaves us with the part that is about what's changing in these 2 reactions, which is I minus. 0.084 raised to the Y and 0.042 raised to the Y. This is just a number so I can plug them into my calculator. Remember, just a reminder, depending on how your calculator works, it has an exponent button that you should use, because if you divide these by writing times 10 caret -4, if you do that, it's gonna kind of divide things funny. So if you use the exponent button, it will work much more efficiently for you. So if I put this in, it's actually an even 2. Okay, it's exactly 2. So on the left side, this simplifies so that it's 0.084 raised to the y, of course. We have that here, and 0.042. Now, since both of them are raised to the y, we can pull that out of here. And all of that equals 2. So this is a lot simpler to work with. The whole point of the method of initial rates is the way that it's structured, the way that we choose the concentrations. It's so that things simplify, right? So I can do the work in the parentheses, and we get 2 again, right? So this boils down to 2 raised to the y equals 2. Now, obviously, it's easy to figure out that y equals 1 from this point, but in the future, we're going to have, and especially in the lab, we're going to have a situation where these numbers are not whole numbers, in which case we can use log to solve it. We just take log of both sides. You can do log or ln, I don't care. And when you do that, it allows you to pull the exponent down, because the logarithm is the opposite function of exponent. I'm going to make a screen here, so ln2, oh, I gotta change it. Oh no, it's already red. There we go. So what we have here is ln of 2 raised to the y equals ln of 2. Okay, or again, you could do log, that's okay. They're going to function the same way, it doesn't matter. Oh, that's 2 raised to the y, sorry. Okay, so when you have the log of an exponent, the exponent comes right out of that. They cancel each other out, so it becomes multiplication. Y times ln2 equals ln of 2, right? And of course, you're going to divide by ln of 2 to get y on its own, right? So y equals ln2 divided by ln of 2. You could plug this into your calculator, but anything divided by itself is always 1. So that one's pretty easy. So now we know that the y value is 1. For the other concentrations, so for the x, we end up with a ratio between, I think, reaction 2 and reaction 3 is what we said. Okay. So what I want you to do is, to finish this, I want you to find the value of x. You can do this in your notes. I'm going to take a look at it in class. Okay, but it's going to be basically the same process as finding y was in this case. Remember, this is made up data, it's not real, okay? I just made up numbers that were convenient and round because it's easier to show you that in the beginning. In reality, 2 is not, it's not ever going to be a whole number, okay? We're going to have to average it or round it at the end. All right, so that's the idea of the method of initial rates. Here's a summary, okay? I'm just going to make up numbers. Let's say that, well, we figured out that y equals 1 here, and I'm just going to pretend like x equals 3. You can solve it yourself. Whatever you got is fine. You can answer this next question with your answer, or you can copy what I write. I don't care. So what we're going to do is we're going to take one of the reactions. It doesn't matter which one. I'll just pick the first one. And we got to try to find k. So I'm going to substitute everything that I already know and solve for k, because that's the last variable. Okay, so we know x, we know y, using this method. K is the last thing. So if the rate is 6.6 times 10 to the negative 4, I'm trying to find k, I don't know it yet. And my concentration is 0.042 for my persulfate. And we said that one was 3, that's the x, and it's 0.084 for that one. Is going to be raised to the 1. So now all I got to do is a little bit of algebra, right? 0.042 cubed times 0.084. And so that's a really little number. And I'm going to take that 6.6 times 10 to the negative 4, so I'm using the E button again, divided by my answer, which is 0.00006, right? Our final K value is 106. This has weird units. We're never going to worry about units. This is the only time I'm ever going to tell you, don't worry about units. Forget it. They're weird. Okay, so we're just going to leave them off. Oh, and another good news. So here's our good news. Units don't matter. Not really, anyway. If we are given units, we can derive some information from that later, but for the most part, units don't matter to us. And the second fact is sig figs aren't that big of a deal. Okay? That's because when we use logarithm functions, the number of sig figs depends on the operator, and it's a lot of math. We're not going to focus on that too much here. I want you to focus on mastering the method of being able to find x, y, and k. Alrighty, so it's a great idea to practice this before lab. You have a pre-lab that's going to be graded where you need to do this. Alright, and of course your lab report is going to do the same thing 16 different times. Don't worry, we're going to use Excel. No big deal. Okay, but you've got to be able to do this mathematically on paper before we can use Excel, so make sure you practice. Okay, so the rest of it we're going to cover in lecture. Feel free to come in and ask me questions if you have any.